Hello everyone, welcome to our webinar on acoustic topology optimization using COMSOL Multiphysics. My name is Arpad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at COMSOL and how to set up physics for optimization of an acoustics problem. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. So what is COMSOL Multiphysics? COMSOL is a multiphysics modeling, simulation and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing. To putting together a custom-built application, a COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. Once you've completed your COMSOL simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And today we are going to take a look at the COMSOL Multiphysics package and an acoustics add-on module and an optimization add-on module. The acoustics module is an add-on to the COMSOL Multiphysics software that provides tools for modeling acoustics and vibrations for applications such as speakers, mobile devices, microphones, mufflers, sensors, sonar, and flow meters. You can use the specialized features to visualize acoustics fields and build virtual prototypes of devices or components. For more detailed studies, acoustics can be coupled with other physical effects, including structural mechanics, piezoelectricity, and fluid flow. The COMSOL software contains multiphysics couplings to enable you to evaluate the performance of a product or design in an environment that is as close as possible to the real world. The acoustics module also includes many specialized formulations and material models that can be used for dedicated application areas, like thermoviscose acoustics used in miniature transducers and mobile devices. The multiphysics environment is extended further with several dedicated numerical methods, including the finite element method, boundary element method, ray tracing, and discontinuous Galerkin finite element method. When you expand the COMSOL Multiphysics platform with the acoustics module, you have access to features for specialized acoustics and vibration analysis in addition to the core functionality of the COMSOL software. The second module we are going to take a look is the optimization module, which is an add-on package that you can use in conjunction with any existing COMSOL Multiphysics product. Once you have created a COMSOL Multiphysics model of your product or process, you always want to improve in your design. This involves 4 steps. First, you define your objective function, a figure of merit that describes your system. Second, you define a set of design variables, the inputs to the model that you would like to change. Third, you define a set of constraints, bounds on your design variables, or operating conditions that need to be satisfied. Last, you use the optimization module to improve your design by changing the design variables while satisfying your constraints. The optimization module is a general interface for defining objective functions, specifying design variables, and setting up these constraints. Any model input, whether it be geometric dimensions, part shapes, material properties, or material distribution, can be treated as a design variable, and any model output can be used to define the objective function. It can be used throughout the COMSOL Multiphysics product family and can be combined with the LiveLink add-on products to optimize a geometric dimension in a third-party CAD program. Built-in algorithms handle the problem of performing optimal adjustment of the selected control variables during an optimization study. A number of different strategies are currently implemented in COMSOL Multiphysics. Since we are doing a shape optimization, modifying the geometry, we use a so-called gradient-free optimization algorithm. So this model illustrates an optimization study with the initial geometry. It's an axisymmetric model. The objective is to maximize the sound pressure level at a point of the assembly across a range of frequencies. The geometry contains the air domain and the porous domain, as well as the excitation, which is modeled as an inward acceleration. The best solution is the solution which, as best as possible, satisfies a list of requirements. For a loudspeaker, examples of such requirements could be maximizing the pressure at a certain point in space or across a range of frequencies, minimizing the supplied electrical power, or fixing the sound pressure level at a specified value. There is in general no unique way of defining the best solution. The concept of best depends on both the application and the appropriate design variables. The concept of best is expressed through a scalar metric in COMSOL called the objective function. Substantial care must be exhibited when choosing the objective function, because solely these requirements will be satisfied by the final optimized solution. Different objective functions will result in different optimal geometries and/or solutions. COMSOL enables the inclusion of several independent optimization criteria in a single objective function. To maximize sound pressure level across a range of frequencies, the average sound pressure level across the frequency range from F1 to F2 is a natural choice. Here you can see the formulation for that one. The objective here could potentially be achieved by the existence of a high quality resonance in the frequency range F1, F2. This would not be desirable. To avoid this, another objective is added. You can see that one here, which minimizes the variance sigma squared of the sound pressure level across the frequency range. Here sigma stands for the standard deviation. Control variables as geometric parameters are included. Those would be easy to change when developing a design parameterized by the position P and the weights W1, 2, 3. We added logical bounds to the variables, ensuring that any two geometric control points will not coincide, as this will cause a program error. Only the selected variables can be changed during the optimization study, but they do not all have to be. The choice of control variables is typically dictated by the problem. For a loudspeaker, typical parameters would involve speaker geometry and perhaps material properties. Thus include as control features those parameters which can be allowed to vary within the requirements and specifications for the product. Typically, control parameters must be able to vary continuously. While this is natural for most geometric variables, it may be more difficult for material properties and parameters. It is in most cases advisable not to include material properties as control parameters unless the resulting material can be engineered. So now if we go to COMSOL Multiphysics and look into the model, we can set up the geometry. So we will set up geometric properties. So here I opened up a prepared model. So we have the parameters. Not all parameters will be used, but here are some. The radius that can be changed, the height of the resonator chamber A0, it will be the boundary condition for the inward acceleration, and we have some initial weight as you would see before, W1, 2, 3. We have some parameters for setting up the correct mesh sizes. The number of frequencies that we are looking into is 100, and that's for all now. So from geometry part, we will set up some Bezier polygons. First we add the linear term. from 0, 0 to capital R0, then we add the quadratic one from R0 to 1.1 times param, so the geometry can be changed easily, times R till capital H, and from R times this parameter till capital H. Okay, the weights are W1, W2 and W3. Okay, so the solver can change these variables freely. Add another quadratic term, param R over 2, param times H. Okay, and 0 H. And the weights are the same. So W1, W2 and W3. Okay, and then to close this we add the linear term from 0H to 0, 0. Okay. Then we add the linear term that will be used to define the inward acceleration, so that will be used for the boundary condition. So this is also a parameter. Okay, and we need to convert these curves into solid domains. So we need to convert to solid. Okay, and we use a small scaler to scale down this geometry to get the porous domain that will be used here. Transformation, scale. This one, we need the original one. And now it's a constant value, but it can also be a parameter, so you can add bounds to this one. So this outer layer will be the porous domain, and inside this domain will be used as the regular air domain. Okay, so we have the materials, so we have the air, that's from the built-in library, pressure acoustics, so we need the poroacoustics domain here at the outer boundaries, and here you can see there are several built-in parameters and models for poroacoustics models. We will use this one, the default setup with some default settings, but the constants are for glass fiber, so we need a small change to this one. So this is the porous domain, the rest is the pressure acoustics, we have the axial symmetry, and we need an inward acceleration, so we need the normal acceleration as a boundary condition that is applied to this little boundary, and that's a constant value, it's A0, but it can be also parameter, whatever your choice is. From the mesh size, it's important to get a correct size, so we need to set up the minimum and the maximum values. href means that we need at least, if we go here, we need at least 6 elements per wavelength. That's essential for acoustics calculations. Okay, so this is the finite element side, and now we go to the objective functions. So here first we store the pressure to a variable called p stored. That's the intop1. Intop1 is an objective integration operator that acts at a point. So we select this point, so this will store whatever we put into the suffix of this intop1, and since we put P, which is the pressure, to intop1, so we will store the pressure variables at that selected point into a variable called p stored. And from that pressure variable, we can calculate the local sound pressure level with this formula. That's nothing new. And then we can calculate the average of the sound pressure level. So this is the first formula that we applied here. So if we go back, this is the first formula that we want to calculate. So with the with operator, we summarize all the sound pressure levels for all the frequencies, and then we make a summation, since currently no integration is supported with this solver type. And then to set up the second one, the variance that is defined here, so we set up the variance calculation like this. So from the local sound pressure levels, we divide the average, and we make the same with operation to access the solution of the solver, and we make a sum of those frequency variations. So that's the second formula. So that's how we define this inside COMSOL Multiphysics. Okay. And here in the study nodes, we have an optimization node. We use a so-called gradient-free algorithm, since we are changing the geometry. So this little point is changing from iteration to iteration. So there is no way to describe analytically the objective function. So we need a gradient-free optimization algorithm. And our choice now is the Nelder-Mead. So we will use these two objective functions that we defined prior, the average sound pressure level and the variation. And here are the control variables. These are the parameters that can be changed by the solver algorithm during the solution process. So we have these geometrical parameters, capital R and H, and we have these three weights that will be changed during the optimization model. And if we go into the recorded solution process to see how it works, so here on the right hand side you can see the initial geometry, and here on the left hand side you can see how this geometry is changing during the optimization process. So I made a small video to show you how it works. It takes some time to solve, so now we don't have time for that, so we can see the recorded video of the objective and change of these design variables. Okay. So if we go further, we can see that it's changing one by one. Okay. So now if I open up the solved model, we can look into that one. Okay, so this is the final solution. So we can see some initial designs, and on the left hand side you can see the final, the so-called optimized design, and you can see the sound pressure level is a bit changed. And what is more important for us is the response, the frequency response of our chamber, of our device. So we set up a frequency range from F1 to F2, so roughly to 2000 Hertz. And you can see the blue one is the optimized geometry response, and the green one is the initial one. As you can see, we have some deviation, some change and spikes in the response with the initial design, but if we apply those two objective functions, we can create a very nice and very smooth frequency response of our chamber based on our mathematical formulation. And that's the acoustic pressure plot for the optimized and an initial design. So that's the final response. That's what we wanted to achieve, to create a very nice and smooth change across the frequency range. And of course we maximize the response, so we have higher response sound pressure level at those points. So to summarize my points here, so we can see that we have several options to set up these so-called porous domains. You can choose from various built-in models. You can choose from optimization algorithms, whether it's a gradient-based or a gradient-free optimization method. You can add bounds, control variables, and as many of objective functions as you wish. It's easy to do that. And there is a link to the Acoustics module, and there is also a link to this shape optimization of a tweeter waveguide, which is a much more sophisticated and complex model. Here on the right hand side you can see the initial design, and on the left hand side you can see the so-called optimized design. So here there are three different cases. One is for optimizing over a frequency range to increase the average sound pressure level and decrease the variance. That's exactly what we did here. Second one is the optimization for spatial response, and the third one is the optimization for directivity index. So you can use this one as a quick guide to this optimization module combined with the acoustics module. So I summarize this one and I wrap up my presentation. So if you need and if you would like to try out the software or need any more help to set up such problems and models, feel free to contact us, and you can search for archived webinars and videos. And thank you for your attention, and see you at our next webinar.